In this video, we're going to go over determining the domain of functions given the equation. What we've looked at previously is determining the domain and range of functions given their graphs. So I've got a graph here of a function, and just to kind of get our heads back in the game, as far as domain and range goes, domain is all the possible x values. So this is where we scan the graph left to right, and doing so, the first thing we hit is this point, which corresponds to an x value of -4. And so that means the domain is going to start at -4, and since that graph is a solid graph, we're going to use a square bracket. And then as we continue to scan from left to right, the last thing we're going to hit is this arrow. And so what that means is that our domain is going to go on in the x direction forever. So we represent that with an infinity sign, and we always use a parenthesis for infinity. So that's going to be our domain. For a range, we go through the same process, except we're going to be reading the values off of the y-axis. So again, with the range, we want to scan bottom to top, and the reason for that is because interval notation always needs to be expressed the least to greatest. So the first point we hit, bottom to top, is going to be the same one we hit before, but this time we're going to read the value off the y-axis. So that's going to be a -2. And then continuing to scan upward, the last thing we're going to hit is the arrow, and that is pointing in the positive direction for y's as well, and so the range will go on to infinity as well. So that's just a quick review on reading the domain and range off of a graph. What we're going to focus on is reading just the domain, so we're not worried about the range, or determining, is more than reading, determining the domain of functions given their equations. And the functions the equations we're going to be looking at are the ones that are of the basic graphs that we've already talked about and we've worked on graphing. So what I want to do, so we can see what's going on with those, is go back to some of the stuff I worked up when we did the intro to 2D video, and work off of where we had left that when we did the intro to 2D video. In that video, we looked at several graphs of functions, and I've brought up our notes from that video here. So the ones I have on the screen are the constant function, the linear function, the quadratic function, the cubic function. There are more below that we'll scroll down and look at in a second. But earlier we had left the domain and range lines blank, but now that we know how to read the domain and range off of a graph, we can go ahead and fill those in. So, for example, with the constant function, reading that left to right, we have an arrow on the left and an arrow on the right, which is going to give us a domain of -infinity to infinity, because we're reading that back to the x-axis. As far as the range goes, it's a little different because of the nature of a constant function. The only y value there, everything maps back to the y-axis as a 3. So that means the range only comprises of a 3. And the way we say that, we're not going to use interval notation because it's a single value, it's not an interval. So the way we do that is we just use our set notation, because set notation is when we have exact values. So that'll be how we express the range. Now for our linear function, we have arrows on both ends. So reading it left to right, we begin with an arrow and we end with an arrow. So that makes the domain -infinity to infinity. Similarly, reading it bottom to top, we also begin with an arrow and end with an arrow. And so our range will also be -infinity to infinity. Okay, moving on down, looking at the parabola, scanning left to right, the first thing we hit's an arrow on the left, and then we end with an arrow on the right. And it kind of looks like in this picture that that's going to end up shooting straight up, and so it won't keep expanding, but it will keep expanding. Remember, it can't shoot straight up, because if it's shooting straight up, then it's not going to be passing a vertical line test. It's not even a function. So with that, beginning with an arrow and ending with an arrow means our domain is -infinity to infinity. Now the range is a little different. When we scan bottom to top, the first thing we hit is this bottom part of the parabola. And then the last thing is the couple of arrows. So it is going to shoot up forever, so it's going to go to infinity. But this particular parabola begins on the x-axis, so it begins at a y value of 0. That gives us a range of 0 inclusive with the square bracket to infinity. Remember, if it doesn't have an open circle, that's considered a solid dot. Whether or not that dot, that point is bolded in, it's solid there unless it explicitly has an open circle. Alright, moving on to the cubic function. Again, reading that left and right, we hit arrows on both sides, and it does look like it's going to be shooting straight down and straight up, but that's just how this picture is looking. It's because it's going up a lot faster than it's going over, but it will continue to go over in both directions. So our domain on the cubic function is negative infinity to infinity. The range, scanning bottom to top, we hit an arrow at the bottom, we hit an arrow at the top. So the range will also be negative infinity to infinity. And then the absolute value function, scanning left to right, we have negative infinity to infinity. And then scanning bottom to top, it behaves kind of like a parabola, and so its range is 0 to infinity with the square bracket on the 0. Now, I do want to emphasize that's for this particular absolute value graph. If we shifted the absolute value to another location on the grid, as we've done when we've graphed some of these, then that's going to shift where that initiating point is. If we flip it over, then it's going to be shooting down to negative infinity. So its range would be negative infinity to wherever its peak point is. Alright, kind of something similar with the square root function, scanning it left to right. The first thing I hit is this point, and that on this particular graph it has an x value of 0. And then the last thing I hit, scanning left to right, is the arrow. And so the domain of the square root function is going to be 0 with square bracket to infinity. The range, if you look at it going bottom to top, we also hit that point first, and then the last thing we hit is this arrow. And it kind of looks like it's going to end up shooting straight off to the side, but it won't. It'll keep going up. It's just going over a lot faster than it's going up. So the range on this graph is also 0 to infinity. The last graphs we looked at, we haven't actually graphed these, but you need to be able to recognize their equation, recognize their graph, and you're going to also need to be able to determine their domain and range. So here, it's kind of hard to tell looking at the graph what's going on. Well, you can tell, like scanning left to right, the first thing we see is an arrow, and the last thing we see is an arrow. But what the question is what's going on here in the middle. So just by reading it off the graph, it's a little hard to tell. So the easier thing to do to figure this one out is to actually look at the equation of the function rule. So with domain is what x can be. And as we talked about in the previous video, x cannot be 0 because that would cause division by 0. And so we eliminate that from the domain to eliminate the problem. So the domain here would be negative infinity to 0, and we're going to leave 0 out, so we use a parenthesis, union 0 to infinity. Sometimes it's a little hard for people to accept this because the thing we're leaving out is what we're writing twice. But one of the ways I like to try to explain it to get that is we're going to leave out 0, so just on the x-axis, but we're going to have all this stuff to the right of 0, we'll have all the stuff to the left of 0. So if I wrote interval notation for the stuff left of 0, including that open circle, and it's got to be open because we're leaving it out, that would give me this interval. And if I wrote interval notation for all the stuff to the right of 0, including that circle so we could leave 0 out, that would give me this interval. And then of course I have to use my union to unite it into one expression. So hopefully that helps you see why we're the notation that we're using double 0 up because we're excluding it on the left and we're excluding it on the right. Alright, once you see what the domain is and note that the graph is x and y's are symmetric, you can pretty easily get to the result that the range will be the same thing. Alright, so that's all those graphs. So I wanted to do that one just as a quick review on how to read domain and range off of a graph. But the point of our video is to determine the domain given the equation, and the equations that we're talking about are these guys, or any of their possible variations that we've covered. So given this r of x function, can you tell me the domain of it is what we're going to be looking at. So I think it's helpful to keep in mind what the graph of each one of these looks like when you're going about determining the domain. So that's why I wanted to review these. Alright, going back up to the top here, the constant function domain was negative infinity to infinity. The linear function domain was negative infinity to infinity. Now imagine if the constant function was going through a different y value, its domain would still be negative infinity to infinity. Same thing with the linear function. If the line had a different y-intercept or a different slope, so it was slanted more or less, it would still be going, it would still have an arrow on each end, and its domain would be negative infinity to infinity. With a parabola, it doesn't matter where you put it on the graph, it's still going to open up forever, and so its domain is going to be negative infinity to infinity. Moving on down with the cubic function, like I said before, that's going to keep expanding forever, so its domain is negative infinity to infinity. And the absolute value function will expand forever, so regardless of where that's positioned on the graph, I hope you can imagine that it's still going to have a domain that expands forever, so the domain will be negative infinity to infinity. And so what I'm getting at with that, whether I give you this basic function, which I have the graph for here, or if I give you some variation of it, it's still going to have infinite width, and so its domain will still be negative infinity to infinity. So all of these that we've looked at so far, they have a domain of negative infinity to infinity, and if you can imagine any possible variation of them, they're going to maintain a negative infinity to infinity. Now when I say any possible variation of them, I don't mean like flipping the parabola sideways. We don't do parabolas like that. Or, you can have parabolas on their side. I should write it in something other than a highlighter. So this is a possibility in mathematics, but that's not what we're talking about here, because that wouldn't even be a function. So I'm just talking about moving it, shifting it around on the grid as we've done when we've graphed it, or flipping it over as we've done when we've graphed it. So nothing like this. So any of those shiftings or flippings, these domains would still be negative infinity to infinity. So that brings us down here to the square root function and the rational function. These are the only two functions that we work with in this class where the domain is not negative infinity to infinity. So when I'm handing you equations for functions, if it's anything but the square root function or the rational function, then you just know that the domain is negative infinity to infinity. There's not any work to prove it. You just know that x can be anything. Whereas if I give you a square root function, there's going to be some work to do to determine the domain. If I give you a rational function, there's going to be some work to do to determine the domain. One way to think about this is that the domain is what x can be. And so when you have, for example, the one that's still showing here, an absolute value function, you can take the absolute value of any number. It's not gonna, math isn't gonna break. You can do that no matter what. Similarly, like we saw up above with a cubic function, you can square any number. You can multiply any number by another number. There's no way that math's gonna break like that. There are times when math kind of breaks, and the two that we focused on in this class is when we square root a negative number and when we divide by 0. And that shows up in these two functions that have limited domains. The reason why we need to limit their domain is to avoid those places where the math doesn't work seamlessly. So for a square root function, we need to avoid taking the square root of a negative. And for the rational function, we need to avoid division by 0. by limiting our domain. So now that we kind of see conceptually which ones are going to be okay and which ones are going to cause some problems, let's go ahead and do some examples of determining the domain when given the equation. Alright, let's start with this one. Determine the domain of f of x equal to 2x plus 3. So when you're faced with one of these problems, the first thing you want to do is ask yourself, what kind of function is this? This is a linear function, which means it graphs as a line. And as we've seen, the domain of all linear functions are going to be negative infinity to infinity. And that's just something you got to kind of put together by understanding how the graphs work. There's not any algebra to do that will get you to that result. Let's look at another one. This time we have h of x equal to the square root of x minus 3. Now here, this is a square root function. So this is one of the ones that cause us issues. So what we want to do is figure out where the issue would be. In this case, with square root functions, we want to avoid having to square root a negative. In other words, we want the stuff under the square root to be positive or 0. So we're going to take the material that's under the square root and set it greater than or equal to 0. So that we want that stuff to be positive or 0, that's when it's okay. So we set it greater than or equal to 0, and then we solve the inequality we have there by adding 3 to both sides. And so then that's going to give us that x needs to be greater than or equal to 3. Now you might just see it with this one. Some of them are harder to see than this one, but so you'll need to actually do the algebra. But if you can see what x needs to be to keep under the square root positive, then you can just go straight there. So last thing we need to do is express this as interval notation. So if x needs to be greater than or equal to 3, then that gives us a domain from 3 to infinity with a square bracket on the 3. Alright, let's do another example. Here we have g of x equals negative 2 times the quantity x minus 4 squared minus 5. Now again, when you're faced with these, you first want to step back and ask yourself, what kind of function is this? This is a quadratic function, graphs out as a parabola. So are there any issues with the math here? No, we can do, x can be anything. None of the math's going to break here. Or you can think that a parabola is infinitely wide. Regardless, we can go straight to knowing that the domain is negative infinity to infinity. Alright, now we have k of x equal to 5. This is a constant function. So if you can imagine a constant function in your head, you could probably even imagine the graph of this particular one. It's infinitely wide, which means its domain is negative infinity to infinity. Alright, I'm going to try to trick you on the next one. Let's say we have x equal to 6. What would the domain of that be? The reason why this one's tricky is because it's not one of the general functions we've learned. We've learned how to graph this. But this actually graphs as a vertical line. So, I mean, you can still determine the domain of any relation. It doesn't have to be a function. But here, remember, the domain is what x is. Well, this equation just tells us straight up what the domain is. Here, x is 6. That's it. X equals 6. And it's a vertical line that's just going through that one x value. So the domain, and we need to use our set notation, is just going to be at 6. Alright, let's try a few more. Let's go with a of x equal to 3 over the quantity x plus 2. So in this case, we have a rational function, which means we need to watch out for the denominator being 0. We cannot let the denominator be 0. This is not saying that we can't let x be 0. We cannot let x be a value such that the entire denominator is 0. In other words, we cannot let x plus 2 equal to 0. So to figure out what our domain is we take the denominator and we set it not equal to 0, and then we figure out what x value would make that the case by solving. In this case, we would solve by subtracting 2 from both sides. So x cannot equal -2. If x were -2, that would make the denominator 0, and that would cause problems. So the domain is everything but x equal to -2. So the way we would write that in interval notation is it would be -infinity to -2, leaving out the -2 on the left, union -2 to infinity. So that's going to be our domain. Alright, I'll do a couple more examples and then I'm going to let you go to try some on your own. Alright, let's say we have b of x equal to 2 times the square root of 2x plus 5 and then -6. So this is a little bit more complicated of a square root function than we looked at before, but it's still a square root function. And this means that we cannot let the stuff under the square root be 0. The rest of the stuff doesn't matter. What we can't we can't let the stuff under the square root be a negative. So that's what matters. The stuff outside the square root would be fine as long as what's under the square root comes out as a positive or 0. So we need to take just the stuff that's under the square root and set it greater than or equal to 0 so that it's going to be positive or 0. And then we just solve this inequality to determine what x value would make this work out. So we subtract 5 from both sides and then we divide both sides by 2. So that's going to give me an x greater than or equal to -5/2. So this tells me what x can be. As long as x is bigger than or equal to -5/2, then my square root, the argument under the square root is going to be positive. So my domain would be -5/2 with the square bracket, because we can include that, to infinity. Alright, let's do one more. Let's look at c of x equal to 3x plus 1, all of that divided by x squared plus 6x plus 9. So we have a rational function. The issue here would be division by 0. What happens in the numerator does not matter. I just need to make sure that the denominator does not equal 0. So I set up what I don't want. I do not want x squared plus 6x plus 9 to equal 0. So then I need to solve this quadratic. It's an inequation, I guess, but we need to solve it to determine what x can't be. In this case, since it's quadratic, we can employ one of our quadratic methods. I tend to factor if possible, and then if not, resort to the quadratic formula. Fortunately, this one factors as x plus 3 times x plus 3, and that cannot equal to 0. Now those x plus 3's are going to produce the same solution, so we only just need to focus on one of them. So we can say x plus 3 cannot equal 0. So to solve that, we're going to subtract 3 from both sides. And so x cannot equal a -3. X can be anything but -3, so the way we would say that in interval notation would be -infinity to -3 with a parenthesis, union, parenthesis, -3 to infinity. The infinities always have parentheses. Alright, so that's a lot of the different kinds of variations that you'll face. Go ahead and give some of these a try and see how you fare.